Hello students, this is a second lecture on instruction sets. Already we have seen different types of instructions: data type, arithmetic, branch, loop, machine control, flag, shift and rotate, string instructions. Had a detailed discussion about data and data transfer instructions. Today we will discuss about arithmetic instruction. So in this we will be discussing about addition, subtraction, increment, decrement kind of instructions. In arithmetic instructions, first instruction is add destination comma source. Add destination comma source is a structure of an instruction. In this instruction, two operands will be added. So destination will be the final result where the process after this instruction will be stored. The examples of this instruction are add ax comma 2020, whereas this 2020 is added into ax and final result will be stored into ax only. The second example is add ax comma bx, where the contents of bx are added into ax and the result will be stored into ax. Ax is considered always as an accumulator, as a final destination or the storage. It's a default storage after every execution. This is an example with which we will be able to understand how it works. As far as first instruction is considered, instruction ax comma 2020, h will contain 10 and al will contain 10. So this is the contents of ax. So then 1010 will be added to 2020 and the result will be stored in ax. Here the second instruction is add ax comma bx. Contents of ax are 1010 and bx are 2020. So after execution of this instruction, the 1010 will be added to 2020 and final result 3030 will be stored in ax. This is what it can be seen very easily. The final contents after addition of ax comma bx will be stored into ax only. So the previous contents of ax 1010 are altered to 3030 as a final result. The second arithmetic instruction is ADC. It has a structure like ADC, destination comma AX. The destination and source can be a register or a memory location also. In this instruction, the contents of source operand with the contents of destination operand with a carry flag. So this addition, in this instruction, the addition will be done as a regular addition, but if the carry flag is set, then that carry will be added into the final result. The source may be immediate data, memory location or register, whereas destination is memory location or a register. The result is stored in the destination operand. AX is a default destination register. This is an example. ADC AX comma 2020. Here the carry flag is set 1. So the 2020 contents will be added into AX, which has 1010, and then the carry flag will be added into this. The second example is ADC BX AX comma BX. Contents of BX will be added into AX with the carry. The final result is 1010, the contents of AX, 2020, the constant will be added here, and the result is 3030. In this result, carry 1 is added and will get final result as 3031. So this will be stored into AX. The same way we have the contents for ADC AX comma BX. So the addition is here. So 3031. Another arithmetic instruction is increment source. This is a general increment operation. With this, the contents of the register will be incremented by 1. This instruction increases the contents of source operand by 1. The source may be a memory location or a register. Source cannot be immediate data. The result is stored in the same place. So increment AX and increment memory location 5000H are the examples. The example of this 1010 increment in AX register will be done here. So AX has the contents 1010, it will be incremented. The memory location 5050 contains the value 1010 here, and this will be added, incremented by 1. So increment 1 means the contents of AX register 1010 are incremented to 1011. Same here, the contents of at 5000 location are incremented by 1. So 1010 will be incremented to 1011. The next arithmetic instruction is decrement source. This instruction decreases the contents of source operand by 1. The source may be a memory location or a register. Source cannot be immediate data. The result is stored in the same place. So decrement AX is an example. The another example is decrement memory location 5000H. So this is the example. So AX contains 1010. After decrement EX will reduce or subtract 1 from the contents. The another example is decrement 5000th location. At 5000 location, it has 1010 contains that will be incremented. So this 1010 will be decremented so that we will get a value 100F. The same here, 1010 at the memory location 500 will be decremented by 1. One value is subtracted, and that is 100F are the contents. Subtract destination comma source. This instruction subtracts the contents of source operand from the contents of destination. The source may be a immediate data, memory location or a register. The destination may be a memory location or a register. The result is stored in the destination place. So subtract AX, 1000H. This 1000H immediate data will be subtracted from AX, and the result will be stored at AX only. Subtract AX, BX will subtract the contents of AX minus BX, and the result will be stored at AX only. So this is the example. So AX, 1000H. So AX will have the value 2000, and this 1000H is subtracted here, and the final result is 100H will be available at AX. Subtract AX, BX. AX will have the value 2000, BX will have the value 1000. After subtraction, we will get the value 10000, that is in AX register. Here the same, the contents, the final result will be stored at AX 1000H. The next instruction is SBB. This instruction is subtract with borrow. This SBB destination source is the structure of writing the instruction. This instruction subtracts the contents of source operand and borrow from the contents of destination operand. The source may be a immediate data, memory location or register. The destination may be a memory location or a register. The result is stored in the destination place. SBBAX, 1000H. This 1000H will be subtracted from AX and also the borrow. The final result will be stored at AX. Same with this, contents of BX are subtracted from AX and the borrow will also be subtracted from AX and the final result is stored at AX. This is how the instruction executes. SBBAX 100 is subtracted. We have a borrow here, so this borrow will also be subtracted. We will get a final result 2020 minus 1000. Final result is 1020 and the borrow minus 1 is subtracted and then we will get a final result of 1019 and that is stored it at AX 1019. Same with this case. Then the next arithmetic instruction is very important. This is a compare instruction. So this compare instruction has a destination comma source. This instruction compares the contents of source operand with the contents of destination operand. The source may be a immediate data, memory location or register. The destination may be a memory location or register. Then the resulting carry or a zero flag will be set on or reset. This is the result of the comparison. If these two operations 100 is compared with AX, this is the immediate data and the contents of AX register are compared. The same with compare AX comma BX. It can be seen here, compare AX comma BX, destination and source. Destination and source, if both are equal, then the result of comparison will be 0. So, 0 flag will be set. If destination is larger and source is small, then no carry flag or 0 flag will be set. If the destination is smaller than source, then carry flag will be set and 0 flag will be 0. So, here we have AX as a destination and BX as a source. So, AX and BX both are same. So, we will get 0 flag as a set. Then we have to compare AX comma BX. Here the AX is a larger, means the destination is larger and BX is a small. So, we will get nothing set as a flag. Here the destination BX is a larger than AX. So, we will get the carry flag set as a result of this comparison. The AX and BX will not be altered, they will remain the same even after execution of the instruction. The next arithmetic instruction is AAA. This instruction is a special instruction. This is its own structure as a AAA. It does not have a source and destination. This instruction is executed after ADD, that is add instruction. This instruction is known as ASCII adjust after addition. So, whenever the add instruction is executed, then if we want to adjust it for the ASCII, then this instruction will be executed. If lower bits of AL are less than or equal to 09, then higher bit of AL should loaded with zeros. There should be no change in lower bit of AL. AH also must be clear. So, this is the result. AH is 000000H. If lower bit of AL is greater than 09, then bits of AL must be incremented by 6. So, AL plus 0, 1, 1, 0, it means 6 will be added to that. Bits of AH must be incremented by 1. So, AH will be 0001. Then the higher bits of AL should be loaded with 000H. This is what carried out when one AAA instruction will be executed. This is how it works. If AL is less than or equal to 09, then the execution result will be 6 and 7 for a higher byte and lower byte before execution, and after execution this is 0 and 7. Another case, if AL is greater than 09 after addition, then the 6 will be added into that and higher bit will be set to 0. This is the final result after execution. If it is 6A, then it will be converted to 00. AAS, the next instruction. This is ASCII adjust after subtraction. It is one and the same like ADD instruction, AAA instruction. So this instruction is executed after subtraction. If lower bit of AL is less than or equal to 0, then higher bits of AL should be loaded with zeros. There should be no change in lower bit at AL. AH also must be cleared. So if lower bit of AL is greater than 09, then bits of AL must be decremented by 09. Bits of AH must be decremented by 01. Then the higher bits of AL should be loaded with 0000H. This is the example. Here, if AL is less than or equal to 09, so yes, it is. So that is why after execution we will get the result as a 07. If AL is greater than 09, then 06 will be subtracted and we will get a final result as a 04 after execution. Then the next instruction is ASCII adjust after multiplication. This instruction is executed after multiplication instruction. Then AH is equal to AL is by 10 and AL is a remainder. So this is an example, move AL, 04, move BL, 09. So this example says that 04 is stored at AL. This is like AL is equal to 04. 09 contains are stored at BL. So multiplication BL. So this instruction works like BL multiplied by AL. So it means 04 multiplied by 09, the result is 36. So after execution, so the 36 will be stored something like 03 and 06. But after execution of AAM instruction, after execution of this instruction, that will be adjusted to ASCII. Arithmetic AAD instruction, ASCII adjust before division. So this instruction will be done after division instruction, before it goes to division. So AL is equal to AH multiplied by 10 plus AL. This is what it has to do as AAD instruction. Move AX, 0105. So this 0105 will divide the contents, move the contents into AX. AAD instruction will adjust it like AL is equal to 15 and AH is equal to 00. We have the next instruction as a DAS instruction, decimal adjust after subtraction. If lower bit of AL is less than is greater than 9, then AL is equal to AL minus 06. The contents of AL will be altered. The example is move AL, 30H, move CL, 20H. The contents 30 will be added or assigned into AL, and the same 20 contents will be assigned to AL. Subtract. After subtraction, the contents of CL will be subtracted from AL, and the final result will be stored at AL, that is 0A. DAS, the contents will be decimal adjust after subtraction, will convert it into decimal. So AL will have the contents as 0A, 06 will be subtracted from that, so we'll get a final result as a 04. Then the next instruction is multiplication and the operand. This is unsigned multiplication. Operand contents are positively signed. Operands may be general purpose register or a memory location. The result is stored into accumulator finally. So the example of this multiplication instruction is AL is MULBH. So when the operand is a byte, then AX is equal to AL multiplied by operand. If the operand is word, then the result will be stored into DX if the operand or the result is more than AX or 16-bit. So if 8-bit multiplied by 8-bit, if the result is more than 8-bit, then the remaining will be stored into AH. Here, if the result is more than 16-bit, then the result will be stored in AX and the remaining will be stored into DX. So the example is MULBH. So contents of BH will be multiplied with AL, and this is how we get the final result as a AL into BH. The result is more, that is why it will be stored into AX finally. CX, MULCX. So contents of CX will be multiplied with AX and the result will be stored into AX only. The example can be seen for IMUL operand. So this IMUL operand is signed multiplication. So operands contents are negatively signed. Operand may be general purpose register, memory location or an index register. If an operand is of 8-bit, then the multiplication it contains into AL. If the operand is 16-bit, then multiply it with the contents of AX. The result is stored into accumulator. Same as MUL, but this operation is signed multiplication. IMUL BH, the contents of BH will be multiplied with AL and the result will be stored into AL. If it is larger, then it will be stored into AX. The IMUL CX will multiply the contents of CX into AX and result will be stored in AX, if larger, into DX. Division instruction, DIV operand. This is a structure. This is an unsigned division operation. Operand may be a register or a memory location. Operand contents are positively signed. Operand may be general purpose register or a memory location. AL is equal to AX operand if it is 8-bit, and the remainder will be stored into a AH for 8-bit. Move AX, to 0 to 03. The 0 to 03 contents will be assigned to AX register. Move BL, 04. DIV BL. So this 04 contents of BL will divide the contents of AX, that is 0 to 03. After division, we get a final result as here 80. The AL will contain 50 and AH will contain 00. This is the signed division. After unsigned division, we have another instruction as IDIV operand. The signed division, this operand may be a register or memory. Operand contents are negatively signed. Operand may be general purpose register or memory location. This is when the operand is a byte, then AL is equal to AX, or a operand AH is a reminder where we store it. When the operand is a word, then AX is equal to DX EX or a operand. DX is a reminder where we store it. So move AX comma minus 0 to 03, move BL comma 04. So 04 will divide minus 0 to 03 and we will get a final result here. This is how we have studied 8086 microprocessor arithmetic instructions. We will study the remaining in the next lecture. Thank you.